Okay, good afternoon, children. In the last class, we had discussed about the two types of mechanisms that comes under nucleophilic substitution reaction, right? Sn1 mechanism and Sn2 mechanism. Rijas, can you tell me the features of Sn2 mechanism? Yes, Sn2.
Second order kinetics. Follow second order kinetics.
Little more louder.
It follows second order kinetics.
Okay, it follows second order kinetics.
We have one step.
Okay. Second order kinetics. Then how many steps are there for Sn2 reaction?
Only have one step.
Okay, only one step. That means the bond breaking and bond formation take place simultaneously. Okay, then what about the reactivity?
The reactivity order is primary greater than secondary greater than tertiary.
Yeah, what's the reason?
Because secondary and tertiary are bulky.
Yeah, bulky substituents are there, so steric effect will be there. So it is difficult for a nucleophile to attack this carbon. Okay, that's fine. Then Evelyn, can you tell me some features of Sn1 mechanism?
It follows first order kinetics.
Okay, it follows first order kinetics. Then
And it takes 2 steps.
I can't hear you. Yes, tell me. Not audible, Evelyn.
2 steps.
Try once again.
2 steps are involved.
Voice is too low. I can't hear. Yeah, Aditya. Features of Sn1 mechanism.
And follows first order kinetics.
Okay.
Takes place in 2 steps.
Okay.
Then tertiary greater than, secondary greater than
Primary. Okay. And in the case of Sn2 mechanism, inversion of configuration is there. Okay. Then now we are moving to the stereochemical aspects of this nucleophilic substitution reaction. Stereochemical aspects of nucleophilic substitution reaction. Okay, stereochemical aspects of nucleophilic substitution reaction. And the first term is optical activity. Optical activity. Optical activity. Okay, before learning this, can you tell me what about the direction or dimension of this ordinary light? The direction of propagation of ordinary light. In all directions or in a single direction? Ordinary light. It has dimension in all directions. Okay, ordinary light. When this ordinary light, it is passed through Nicol prism, it will be changed into a plain polarized light. Okay, plain polarized light. That means this light has only dimension in only one direction. Okay, dimension only in one direction. So when an ordinary light, it is passed through a Nicol prism, it will be converted to a plain polarized light. Okay, plain polarized light. And this plain polarized light, it's again passed through certain solutions of compounds. It is rotated. It is rotated. Such compounds are called optically active compounds. And this phenomenon is known as optical activity. I will repeat it once again. The plane of plain polarized light. That means the plain polarized light, it has the propagation of direction of propagation only in one direction. the plane of such plane polarized light, it passes through solutions of certain compounds. Okay, it will be rotated. Such compounds are known as optically active compounds. And this portion, yeah, this is how this plane polarized light is produced. Clear, children? Yeah, Chud, what's your doubt?
Is this the one we learned in the last chapter?
Yes, same thing. Okay, yes. So, this plane polarized light, it is produced by passing ordinary light through Nicol prism. So, the plane of this plane polarized light, it is rotated when it is passed through the solutions of certain compounds. Such compounds are called optically active compounds. Do you remember the two types of optical activity that we have learned in chapter biomolecules? Yeah, Aditya. I think you are ready to. Very good. Dextro and levo. Okay. It's rotated either to right or to left. Okay. If it is left, it is levo rotatory. If it is to right, it is dextro rotatory. These are the two types of optical activity. So this plane of plane polarized light that is produced by passing ordinary light through Nicol prism is rotated when it is passed through solutions of certain compounds. Such compounds are called optically active compounds, and this phenomenon is known as optical activity. And the angle by which the plane polarized light is rotated, it is measured by an instrument. It is called polarimeter. Okay, how much is the rotation of this plane polarized light towards the right or left? It can be measured by an instrument called polarimeter. Clear?
Ma'am,
Yeah, Gauri.
what is the meaning of plane polarized light?
That 1 minute. Yes, that means the ordinary light when it is passed through this Nicol prism, you can see that here the direction of propagation of this ordinary light like this. When it is passed through certain Nicol prism, it will propagate only in this type. Okay, when this light is passed through Nicol prism, it will be propagate only in one direction. This light is known as plane polarized light. It will be polarized only in one plane. That's the meaning. And the plane of this polarized light, it will be passing through certain solutions. It will be rotated either to right or to left. Okay. Such compounds are known as optically active compounds, and this phenomenon is known as optical activity. And the instrument used to measure the extent of angle by which it is rotated, that is polarimeter. Have you completed this slide?
No, ma'am.
Okay. Completed, children? All of you, right?
No, ma'am.
No? Okay.
Okay, ma'am.
Okay. Then, if the compound rotates the plane polarized light to the clockwise direction, Okay, clockwise direction or to left, right. It is called dextrarotatory. Okay, clockwise direction or to right, it is dextrarotatory or the D form, and it is indicated by placing a positive sign before the degree of rotation. I told you optical isomerism or optically active compounds, they are in two types, dextrorotatory and levorotatory. If this rotation of plane polarized light either towards right, it is known as dextrarotatory or D form or plus positive sign also indication of this dextrarotatory. Okay. Then if the light is rotated towards anti-clockwise direction, the compound is said to be levorotatory or the L form, and a negative sign is placed before the degree of rotation. So such this plus form and minus form or the D form and L form, these isomers of a compound are called optical isomers, and this phenomenon is termed as optical isomerism. Optical isomerism. Isomer means they have the same formula but difference in certain features, right? Here the rotation is different for two compounds. Their molecular formula is same, but their certain features will be different. Here the rotation will be different. One is rotated in clockwise direction, other in anti-clockwise direction. Vidur, can you read the points?
If the compound rotates the plane polarized light to the clockwise direction, it is called dextrorotatory or the D form, and it is indicated by placing a positive sign before the degree of rotation.
Okay.
If the light is rotated towards the anti-clockwise direction, the compound is said to be levorotatory or the L form, and negative sign is placed before the degree of rotation.
Okay.
Such plus and minus isomers of the compound are called optical isomers, and the phenomenon is termed as optical isomerism.
Okay, phenomenon is termed as optical isomerism. Emmanuel, Shivani, Aryan, Lydia, Nia, Anthony, Steffi, Gayatri, Navrin, Srihari, all of you switch on your videos. Finished? Achyut? Yes. Vidur?
No,
Okay, complete.
yes, ma'am.
Okay. Then next one is molecular asymmetry, chirality, and enantiomers. Okay. Another terms in the stereochemical aspects, molecular asymmetry, then chirality and enantiomers. Molecular asymmetry, chirality, and enantiomers. So here crystals of certain compounds, they exist in the form of mirror images. Okay, crystals of certain compounds, they exist in the form of mirror images. And these aqueous solutions of both types of crystals showed optical rotation. They are equal in magnitude but opposite in direction. Their mirror images are equal in magnitude, but they have, that means optical, when they shows optical rotation, one towards right and other towards left, right? So they have equal in magnitude for the solutions of equal concentration, but opposite in their direction, one towards right, other towards left. So this arrangement of 4 groups around a central carbon, it is tetrahedral. If you look at the example of carbon, you know that valency of carbon, it is 4, right? So we can arrange 4 substituents around the carbon atom. And if all the substituents attached to that carbon, they are different, such a carbon is called asymmetric carbon or stereo center. Okay, asymmetric carbon or stereo center. So this observation of crystals of certain compounds, they exist in the form of mirror images. It was according to the study of Louis Pasteur. Louis Pasteur. Okay, the observation of Louis Pasteur that crystals of certain compounds exist in the form of mirror images. That means one towards right, other towards left. So this aqueous solutions of both types of crystals, they will show this optical rotation. It has equal in magnitude but opposite in their direction. Okay, and this is another term, that is asymmetric carbon or stereo center. Arrangement of 4 groups around a central carbon is tetrahedral, and if all the substituents attached to that carbon are different, such a carbon is called asymmetric carbon or stereo center. When this carbon is surrounded by, here it is one CH3 group, then H, then Cl, then again here CH2, CH3. Okay, CH2, CH3. Then look at the different substituents around this carbon atom. They all are different, right? Methyl group is there, hydrogen is there, chlorine is there, ethyl group is there. So arrangement of 4 groups around a central carbon, it is tetrahedral. And if all the substituents attached to that carbon is different, it is considered as a asymmetric carbon or stereocenter. Symmetric means they are similar, right? They are equal. But here, the 4 groups are different. That's why this carbon is known as asymmetric carbon or stereocenter. So a molecule with this asymmetric carbon, it is known as asymmetric molecule. Okay, a molecule which possesses asymmetry in its structure, it is known as asymmetric molecule. Clear, children? So these are the 2 conditions to consider this carbon as asymmetric or stereocenter. Arrangement of 4 groups around a central atom, it will be in tetrahedral, and all the substituents attached to that carbon are different. Okay, such carbon is called asymmetric carbon or stereocenter. Then according to the suggestion of this Louis Pasteur, he concluded that these similarities, that means the crystals of certain compounds, they exist in the form of mirror images. This property, it is due to asymmetric carbon or stereocenter present there. Okay. So crystals of certain compounds, they exist in the form of mirror images. And he told that it's this optical rotation, they have equal in magnitude but opposite in direction. And this asymmetric carbon or stereocenter, it is considered as one of the reason for this optical rotation in compounds. Okay. This is clear? Dia, can you please read the points?
Crystal of certain compounds exist in the form of mirror images. Aqueous solutions of both types of crystals showed optical rotation equal in magnitude but opposite in direction. Arrangement of 4 groups around a central carbon is tetrahedral, and if all the substituents attached to the carbon are different, such a carbon is called asymmetric carbon or stereocenter. Asymmetric molecule.
Yeah. Have you completed, Achud? Yes, okay. Then, okay. Then this asymmetry of the molecule along with known superimposability of mirror image. You look at the image given here. This is known superimposable mirror image. Okay, these are the mirror images of our hand, right? It is non-superimposable in nature. When you place one above the other, it cannot be superimposed. That's why it is known as non-superimposable mirror images. So the compounds with this asymmetry of molecule along with non-superimposability of mirror images, it is responsible for the optical activity. We already learned factor, that is the asymmetry of molecule. Along with that, non-superimposability of mirror images, these two are the factors responsible for optical activity. Okay, the asymmetry of molecule along with non-superimposability of mirror images. Okay, you just imagine a compound with symmetry. Okay, this is a carbon. Then all groups are considered as CH3. Then if we rotate it either to right or left, it will remain same, right? So it cannot able to shows optical activity. If it rotates to either right, it cannot be considered as dextrorotatory, or if it rotates to left, it is not considered as levorotatory because all the substituents are same. We cannot differentiate this. And the same thing, if we are making a mirror image of the same compound, it will be same to the previous one, isn't it? Yes. So these two reasons are the factors that are responsible for the optical activity. Asymmetry of molecule, non-superimposability of mirror image. These two images are superimposable. Okay. So in the case of molecules with symmetry and superimposable mirror images cannot shows optical activity. So you have to note asymmetry of molecule along with non-superimposability of mirror images is responsible for optical activity. Clear, children?
Yes, sir.
Okay. Shall I move to next slide? Okay. Then the objects which are non-superimposable on their mirror images, they are said to be chiral molecules. And this property is known as chirality. Okay. The objects which are non-superimposable on their mirror images are said to be chiral, and this property is known as chirality. Chiral molecules or chiral. And these chiral molecules, they are optically active. Chiral molecules, they are optically active because they have non-superimposable on their mirror images. Then objects which are superimposable on their mirror images, they are called achiral. Okay. Objects which are superimposable on their mirror images are called achiral. Then this achiral molecules are optically inactive because they have superimposable mirror images. They cannot show this optical activity. Then you look at the examples given here, non-superimposable and superimposable objects. In the case of sphere, when you take the mirror image of the sphere, it will be looking similar, right? Same in the case of a square, triangle, cone, etc. But in the case of hand, it is non-superimposable mirror image because the thumb finger, it will be in different direction. Not only thumb finger, all other fingers. They are in opposite direction compared to the next one. So the objects which are non-superimposable on their mirror images are said to be chiral, and this property is known as chirality. Then chiral molecules are optically active. Objects which are superimposable on their mirror images are called achiral. Achiral molecules are optically inactive. Srihari, can you please read the points?
The objects which are not non-superimposable on the mirror images are said to be chiral, and this property is known as chirality.
Yeah.
Chiral molecules are optically active. Objects which are superimposable on their mirror images are called achiral. Chiral molecules are optically inactive.
Yeah. According to British pronunciation, it is chiral. Okay. I think some others are pronounced this like this, chiral molecule. But the correct pronunciation, it is chiral molecules. Okay, chiral. This is clear, children, about the chiral molecules and achiral molecules.
Ma'am,
Yeah, Vidur?
what are the superimposable?
Yeah, when you place one above the other, one should be hide behind the other. That is superimposable. You cannot able to see that placed in the bottom position. Okay, if you place one circle in the same size and same shape above the other, you cannot able to see the one in the bottom portion, right? That is superimposable. Okay, if it is non-superimposable, that means it can be, if you place one hand over the other, you can clearly see in the thumb fingers, right? That is, it is non-superimposable. Clear? Vidur?
Yes, ma'am.
Okay. Shall I move to next slide? Okay, then we are moving to next one. That is one example that's given in your textbook. First one is propan 2-ol. Okay, propan 2-ol. Here one carbon, then two CH3 groups, OH group there. CH3, CH, OH, CH3. Okay, same thing is represented like this. Then just looking at this A and tell me, is it symmetric or asymmetric? Is it asymmetric carbon or symmetric carbon present in the molecule A, compound A? Tell me. What's the criteria to consider this carbon as asymmetric? Gayatri, can you tell me? Unmute.
Because it's not tetrahedral, like all the valencies are not filled.
Symmetric or asymmetric?
It's asymmetric.
Asymmetric. Here the valencies are filled, but look at the groups present there. Not asymmetric, symmetric. Okay. If four groups are different, that is considered as asymmetric. Here look, you can see that CH3, then CH3, then H, OH, right? The two groups are same. So this is an example for symmetric molecule. Symmetric molecule.
Ma'am, could you say that again, please?
Sure. If the four groups are different, it is considered as a asymmetric. The carbon present here, it is asymmetric. If the four groups are different, it is asymmetric carbon. Okay. Here the two groups are same, CH3 groups, right? So it is considered as symmetric carbon present here. This one is carbon. Then you look at the next example, D. Emmanuel, can you tell me, is this D symmetric or asymmetric? D. These are the groups present there. C2H5, then C.
Asymmetric, ma'am.
Yeah, asymmetric. Because four groups are different, right? Four groups are different. So this is considered as asymmetric molecule. Asymmetric molecule.
Ma'am,
Yeah.
so to tell whether it is symmetric or asymmetric, we should find the mirror image and then we have to rotate it 180 degrees.
Yeah, to find out asymmetric or not, just look at the number, different substituents present in the carbon atom. That's needed. Okay. Then to check whether it is optically active or not, you have to consider both these factors, asymmetry and their non-superimposable mirror images. Clear? Achu? If the four groups are different, it is asymmetric. But if the asymmetry and non-superimposable mirror image there, then it will be considered as optically active. So now we are going to check whether this one is optically active or not. Okay. So the first one, A, it's already symmetric. Then second thing, that's the mirror image of same propan 2-ol. Okay. Second image, that's the mirror image of propan 2-ol. The CH3 groups, they are in opposite side in the mirror image, right? Okay, then again we rotate this mirror image of propan 2-ol by 180 degree. That's the third one, rotated mirror image. Rotated mirror image. Then you just compare A and C. Is it superimposable or non-superimposable? A and C. When you place one above the other, is it possible to clearly see the both compounds? It is considered as non-superimposable. So can you tell me, A and C superimposable or not?
Ma'am,
Yeah.
can you tell the definition again?
For what, Gauri?
Non-superimposable.
That we already written, right? Okay, no need to write the definition. That means if we place, that's not a definition, that's explanation for that. If you place one above the other, you can clearly see both these compounds, then it is considered as non-superimposable. Okay, clear? Then the opposite one is superimposable. We cannot clearly see in both the compounds, that is superimposable. Okay, then tell me, it's already a symmetric molecule. Then look at the mirror images of A and C. Then can you tell me, is it superimposable or non-superimposable? Rijas, can you tell me? Superimposable or non-superimposable? Can't hear.
Non-superimposable.
Non-superimposable? If you place one above the other, you can able to see both the compounds clearly. A and C, not A and B.
Superimposable.
Yeah, right. So it is symmetric, then superimposable. A and C are superimposable mirror images. So can you tell me this propan 2-ol is chiral molecule or achiral molecule? It is symmetric, then superimposable mirror image. The one that shows optical activity, that is considered as chiral molecule. So now you can tell me. Yeah. Gauri.
Achiral.
Yes, propan 2-ol, that is achiral molecule. We can also use the term if completely overlaps, it is considered as superimposable, and if not completely overlaps, it is non-superimposable. Okay. Then look at the next example. That is butane 2-ol. Butane 2-ol. Is it symmetric or asymmetric? Symmetric or asymmetric? Emmanuel? Symmetric or asymmetric?
Asymmetric.
Very good. Asymmetric. Because the fold groups are different. And then the second, the image E, that is the mirror image of D. Okay. E is the mirror image of D. Then we again rotated this E by 180 degree and take the mirror image. Not mirror image, we just rotated this E. Then look at D and F. Then you can tell me it's superimposable or non-superimposable. D and F. D and F.
Non-superimposable.
Yeah, it's non-superimposable. Because C2H5, look at the positions of both this. Here it is C2H5, here it is CH3. When you overlap one above the other, it will be different, right? So it is non-superimposable. Non-superimposable. Here it is SABLE. Sorry, children. Non-super. POSABLE. Non-superimposable. Mirror image. So what about butane 2-ol? It's a chiral molecule or a chiral molecule? Which one? Gayatri?
Molecule.
Yeah, chiral molecule. It has both asymmetric carbon atom and non-superimposable mirror image. Okay. So there are two factors to check whether a molecule is chiral or achiral. That is, first one, non-superimposable mirror image. Then the second one, asymmetric carbon present there or not.
Ma'am,
Yeah, Achu.
propan 2-ol is chiral.
Which one?
First example.
That is achiral.
Okay.
Okay. Because it is symmetric and superimposable mirror image there. So it is achiral. Butane 2-ol, it is chiral. Clear?
Yes, ma'am.
Okay. Have we completed the slide?
Yes, ma'am.
Gauri, what about you? Completed, right? Okay. Okay, then we can discuss the remaining things in the next class. Okay. Then let me take your attendance. Okay, then thank you, children. See you in the next class. Bye.